first step in this process is to prepare plastic samples, plastic sheet samples of a defined surface area with geometry that can easily be inserted into the glass vial. Shown here are low-density polyethylene samples cut to approximately 1/2 inch width that will be placed inside the glass vial for plasma treatment. The samples, minimizing contact with hands by using tweezers, are placed inside the glass vial for treatment. The top cap is then hand tightened across the cylinder. Okay, the next step is to establish the gas composition for plasma treatment. We have compressed air cylinders, one with syn air, which is 80% nitrogen, 20% oxygen, and one with helium. The syn air and helium bottles are fed through two independent mass flow controllers, one for each gas, which then feed into a mixing manifold, which then feeds into a polyline that is connected to a hypodermic needle, which will be used to inject gas through the rubber stopper cap on the glass vial. A second hypodermic needle will be inserted into the rubber stopper to provide a vent. The first step is to set the gas flow ratio to the desired settings and allow the polyline to purge and saturate with the desired gas mixture. In this case, we are using 200 SCCM of helium and 200 SCCM of syn air, as shown on the display here. After a 1-minute purge, the gas flow is established inside the glass vial. The first step is to insert the vent needle into the rubber stopper. The second step is to insert the gas-fed hypodermic needle into the rubber stopper. At this point, the 50-50 gas mixture is filling the glass bottle, and we allow this to continue for 60 seconds in order to appropriately displace the volume of gas in the glass vial with the desired gas mixture. After 60 seconds, the procedure for removing the gas line is to first remove the vent hypodermic needle, followed by the gas-fed hypodermic needle. At this point, the glass vial is sealed and contains the desired mixture of gas for plasma treatment of the plastic sample. The next step is to place the glass vial into the electrode assembly that will be used to provide a AC high voltage for plasma ignition. The electrode assembly consists of a 3D printed plastic form with 2 ring electrodes comprised of spira gasket, which fits snugly around the glass vial to ensure voltage is placed inside the vial and ignition occurs inside the glass vial, not outside the glass vial. The glass vial is inserted in this assembly. The high voltage connections are already established. And the next step is to set up the high voltage power supply to ignite plasma in the volume to treat the plastic. After the vial is charged with the desired gas composition and placed inside the electrode assembly, high voltage is applied using a high frequency power supply coupled to a high frequency transformer to produce peak-to-peak voltages in the tens of kilovolt range. For this demonstration, we will apply a 15 kilovolt peak-to-peak waveform between the 2 electrodes. First, the power supply is turned on. Measurements are made using a high voltage probe and measured using an oscilloscope. This is a 1000 to 1 high voltage probe, so 15 volts equates to 15 kilovolts. At that time, the clock starts for processing, and with the lights turned off, you can see the glow of the plasma treating the plastic samples in the vial. The plastic is treated for a prescribed amount of time, and then taken for analysis. The vial will initially be sent to our metric facility for GC mass spec analysis of gas composition. After the gas in the sample has been analyzed for composition, the vial is brought back to our facility so that the plastic sample can be measured using FTIR and Raman analysis. Those spectrometers are contained at the other end of this laboratory. This part of the video is just a quick tour of the plasma application facilities here at NC State. We're here at the entrance to the lab. Entering, you see we have different gas handling, pressure measurement, and gas delivery components such as mass flow controllers, turbomolecular pumps, pressure controllers, regulators, valves, triple gauges, etc. These are used for a variety of plasma experiments in the lab. The main lab is broken up into 4 different rooms. First room, the counter, is the Plasma Life Science Lab, where plasma interaction with biological materials and is carried out. Also in this lab are 2 spectrometers that are used for the DOE plasma and plastic study, a Raman spectrometer and an FTIR spectrometer. And these are used to characterize the modifications of the plastic films that are treated with the plasma. This is just a storage room. We can probably skip that. This room here is our low pressure plasma lab, where we conduct experiments at pressures below atmosphere. So we have a low pressure microwave source, an inductively coupled RF plasma source, a capacitively coupled reactor used to study cathode shaping and cathode impedance optimization for plasma processes, a second capacitively coupled reactor, and then finally a tube reactor with an inductively coupled antenna, and a toroidal commercial plasma source by MKS Instruments. Most of these reactors operate in pressures ranging from single millitorr range to tens of torr range. The final experiment is actually not a plasma experiment. It is a low temperature liquid metal loop that we use to study electromagnetic pumps for next generation nuclear reactors. The next room is our sample prep room, where we can prepare samples for plasma treatment in a sterile environment. We have a fume hood, a dry box, an autoclave, and various wipes and glass containers that are used for preparation and storage of samples that are going to be treated with the plasma. This is where our plastic samples will be prepared prior to treatment in our plasma reactor. No, you're fine. The last room is our atmospheric plasma room, which also serves as our laser diagnostics room. So we have various atmospheric plasma jets. We have a pulse DC plasma jet here. And we have the experiment and the plasma source that's being used for this work, which we showed earlier, which is our glass vial high frequency AC discharge system for plastic treatment. In addition to this, we also have a neodymium dope YAG laser with an OPO box, which allows us to dial in frequencies ranging from 196 nanometers to 2,500 nanometers for a variety of fluorescence and absorption experiments to study plasma chemistry. Final source is a very high frequency, high power source driven at 162 megahertz, which is used for treatment of materials and is currently being used for the treatment of water for agricultural applications. And that's a quick overview of our experimental facilities that are used, at least in part, for conducting the experiments detailed in our SOPO and in our narrative for this grant.